Welcome to the G Lab. This is Mr. G with another G video about a very important G word, gravity. So let's start with the basics. If you're standing on the earth and you drop something, it's going to go down. But what is down exactly on the earth? Well, it kind of depends on where you are. As you can see from this picture, if you're up here on the earth, down is this way. And if you're down in, say, Antarctica, down is this way. And down can't be sideways and up and down. Down doesn't really exist necessarily. Down is different depending on where you are. So I think what we can probably say more effectively is that gravity is an attractive force, much like myself, but it attracts objects toward something, not necessarily down. It attracts objects and pulls them towards what you'd call the center of gravity, which we'd also call the center of mass. Center of mass is actually a better term for it. And with the Earth, the center of mass happens to be right in the very center. It's the average of all the mass, all the matter that makes up the Earth. That point, it's the average location of all that matter, is the center of mass. And it happens to be in the Earth, in the inner core of the Earth. But there's nothing special about the core. It's not the fact that the core is, molten or made of iron or spinning or creating a magnetic field. None of that really matters. The Earth could be hollow, and the center of mass would be in the same place. There doesn't have to be even anything there for it to be the center of mass. It's just simply the average location of all the matter in the Earth. Nothing about that point is pulling with more or less gravity. It's simply the average location of all of the matter that makes up the Earth. So we can look at this picture and pretty effectively say that there is no down, which sounds like some wise guru spouting off some deep platitude about life, but there really is no down. It kind of depends on where you are. It really is only together. Objects are moving together. They're attracted toward each other. Now, there was another wise guru who sat underneath a tree like this guy, and his name was Sir Isaac Newton. And the story goes, and it's probably a legend, but the story goes that he was sitting under a tree, and an apple fell, and he looked over and thought, oh yeah, gravity. And an apple fell from higher up on the tree, and he thought to himself, well, that's interesting. I wonder how high this tree could be and have an apple up there that was still affected by gravity. Could this tree be 100 feet tall? Well, obviously, an apple would fall from there. What about 500 feet? What about 1,000 feet tall? What about several miles tall? And as he was looking up into the sky at this imaginary tree, wondering if an apple would fall that far, in other words, how far does gravity extend up into the sky, he looked and he saw the moon. And he thought to himself, is the moon affected by the Earth's gravity as well? Is gravity what's keeping the moon in orbit? If so, why is the moon not crashing into the Earth like an apple would? And so this launched him onto his investigation of how gravity works and what it's all about. Now, if we look at the Earth and the moon, which I've labeled conveniently for you, and if you were out in space, floating around between them in this area of space where there's zero gravity, although wait a second, there's not zero gravity. There's gravity from the Earth, there's gravity from the moon. It's just microgravity. You're out there where there's not a whole lot of gravity because you're a long ways from anything. But you're probably thinking to yourself, what is it that actually affects gravity? I'm spinning around and floating. There's basically hardly any gravity, call it microgravity. What affects gravity? There's essentially no gravity out here, and there's also no air out here. So maybe does air affect gravity? When I'm on the Earth, there's air and there's gravity. Maybe air affects gravity. So you radio over to your astronomer buddy, astronaut buddy over on the moon, and he says, hey, there's no air over here either. However, there is gravity. Not a lot, but there's gravity pulling me down onto the surface of the moon. So air must not have anything to do with gravity. Air doesn't cause gravity. The fact that the Earth has an atmosphere, it doesn't matter for gravity. The moon has no atmosphere, but there is gravity. So if air doesn't cause gravity, what does? Well, if you look at the moon, you'll find that it has about 1/6 of Earth's gravitational pull. In other words, if you weighed, say, 100 pounds on Earth, you would weigh 1/6 of that. The force pulling you downward would be about 1/6 of that. So you would feel like you weighed about 17 pounds. You could jump 6 times as high. Pretty cool. If you went to an even smaller rock out in space, Ceres, which is a large asteroid in the asteroid belt in our solar system, you would find that it has about 1/30th of Earth's gravitational pull. You might weigh only 3 pounds or 4 pounds on this little guy. And that means you could jump 30 times as high, or you could throw things 30 times as high into the sky based on their weight. So what is it that's actually pulling things into these planets or moons or asteroids? Well, you can see that it must correspond to something, and it corresponds to perhaps the size of the planet. Well, one more example would be Jupiter. And Jupiter, which is hundreds of times larger than the Earth, doesn't have gravity that's hundreds of times greater than the Earth's. In fact, it's really only about 2.5 times as strong as the Earth. And the reason is because it doesn't have a whole lot of mass. Jupiter is a gaseous planet, and therefore it's very low density and not really all that heavy compared to how big it is. So what is it that affects gravity? Well, you can probably guess it from what we just talked about. It's mass. The more mass an object has, the more gravitational pull it will have. Now, that's great, although that starts to make me wonder, what about this? The Earth has a gravitational pull 6 times as strong as the moon. So if you are on the moon, that means the moon's pulling on you somewhat, but the Earth is pulling on you 6 times as strong. So where are you going to end up going? Well, if gravity's pulling you 6 times as strong toward the Earth, you're going to fall toward the Earth. You're going to get pulled off the moon. But obviously it doesn't happen. We don't see astronauts flying off the moon and falling to Earth. So what's going on there? There must be something else that affects gravity. And by looking at this diagram, you can see that, oh, right, there's a lot of distance between the Earth and the moon. And in fact, this diagram doesn't even show it all that well. This diagram shows them very close together. In actuality, these are the actual sizes compared to each other, but the moon would be far, 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 far away. And so what you see is that, yep, you're way closer to the center of mass of the moon, and so it's going to have a much greater effect on you, even though the mass is only about 1/6, only much less that of the Earth. So distance makes a big difference. It has a huge effect on the amount of gravitational pull that you feel. All right, so mass and distance. Mass and distance. What affects gravity? Mass and distance. This is the key central idea of this entire unit. If you understand one thing, this is the one thing to understand. But of course, this applies and affects many, many more things. So let's take a look at what some of those might be. These large bodies of rock have some serious gravity. What if you took a mountain and looked at its gravity? Does a mountain have gravitational pull? It does. So let's enlarge that slightly to show texture and ask ourselves, how much gravity would a mountain have? Well, it's enough to do some interesting things. This here is what's called a plumb bob. It is a string with a heavy weight on the end of it. Back in the old days, they used to be just a rock on a string, but technology has allowed us to sharpen them and make them pointy. Ooh. Now, what the idea with a plumb bob is this. You want to try and find out what plumb is. Plumb with a B on the end. And what that means is that this hangs straight. I can't say down. It hangs straight toward the center of the Earth, toward the center of mass of the Earth. And it shows you what vertical is. So if you're building a house, for instance, builders use these to figure out what vertical is so they can make sure their walls stand straight up and down, or at least up and down relative to the, so interestingly enough, surveyors use these as well. And surveyors, when they set up their instruments and measure angles to try and figure out property lines or the height of a mountain, or as they survey building sites, interesting things happen if you're surveying near a large mountain. Your plumb bob actually gets deflected. It actually gets pulled toward the mountain slightly by the mass of that giant mountain. It's still getting pulled mostly down toward the mass of the rest of the Earth because the Earth is so huge, but this mountain has enough mass that it actually pulls with gravitational pull the plumb bob, and it deflects it. Now, it doesn't deflect it quite this much, but it does deflect it enough to make a difference in surveying measurements. And in fact, when people were trying to find the height of the tallest mountain on Earth and figure out which the tallest mountain was a couple centuries ago, they were surveying it, trying to figure out how tall Mount Everest was, and they couldn't get an accurate measurement because the Himalayas are so massive. They kept deflecting the plumb bob and messing up their readings on their surveying instruments. Pretty amazing. So planets have a lot of gravity, moons, asteroids, even large mountains have gravity. What else has gravity? Well, anything that has mass.
See this?
Yeah.
You know what it is?
Duh. It's an apple.
Good, good, good. All right, watch this.
What the hell? What is this? What is this, some kind of gag?
No, that's orbit.
Huh?
You have your own gravitational pull.
Oh, that's a bunch of crap.
Now back to the Three Stooges.
Aw. Aw.
So planets, people, baseballs, mice, specks of dust, all objects have gravity. Anything that has mass has gravity. And this is what we call the law of universal gravitation. In other words, we know it's true. It's been repeatedly shown to be true. It's a law, and it applies everywhere in the universe that we've been able to observe. The law of universal gravitation says that all objects have gravity. Anything that has matter has gravity. So let's sum up here. Objects have more gravitational pull when they have more mass. So the larger an object is in terms of its mass, not just its size, but its mass, it has more gravity. So of these two planets here on this giant balance, which one has more gravity? This one here has more gravitational pull. Good. And finally, when they are more near, the distance makes a difference. So more mass and more near, which one of these two planets here is going to be pulled on more intensely from the gravitational pull of this star? Well, it's going to be this one because it is closer. It is more near. It is a shorter distance away. So mass and distance are what affect the gravitational pull of an object. So more mass and a closer distance makes the difference. This here happens to be a sumo wrestler and his young proteges floating around out in space, actually. And you may think that they're trying to push him over, but they're actually getting pulled into him by the gravitational pull of his body. Oh my gosh, he's huge. Check this out. He has a center of mass located right about here. And as you can see, they're all being pulled into that center of mass because of the gravitational pull of him. Now, each of them has a center of mass. And as they float around out in space, their center of mass is being pulled toward his center of mass. And here are some vector arrows that actually show how much they would be pulled. So as you can see, this little guy out here is not being pulled as strongly as these guys in here because he is farther away. The ones who are more near, less distance means greater gravitational pull. Now, interestingly enough, he is also being pulled by them because they have some gravitational pull as well. They don't have as much mass as he does, but they have some. And so he's actually being pulled toward them, all five of them. But where is he being pulled? He's being pulled in various directions, actually. But overall, you could say that his center of mass is going to move towards the average center of mass of these five young men. And so he's going to be pulled toward the average, which is probably somewhere down in here if you were to look at the average location of the center of mass. And he's not going to move very much because he's so huge. His his vector might look something more like this. His center of mass is going to move not much in about that direction right there. All right, so there it is. Gravity, it's what affects it, what causes it, although scientists are still working on what actually causes gravity and how it works. It's not as well understood as you'd think. But we know that the objects that have more mass and that are less distance away will have a greater gravitational pull on other objects. In our next G video, we'll take a look at these vector arrows and learn how to draw them and predict the effects of gravity on various objects. We'll see you next time.